Okay, so last week we were going through logistic regression, and we got to the point where we had set up our cost function, and we were about to go into doing the gradient and actually solving. And we ran out of time basically, and a bunch of other issues. So I decided that today we will continue from there, but for the benefit of those who were not present or who did not have a full understanding, I'm actually going to run just in summary from the beginning again. I'm not going to talk so much about a lot of things I've already explained, especially the logistic function itself, which is a sigmoid function, which I explained. Yeah, but this Jupyter notebook has been shared already, and I believe we all have access to it. So I'll just quickly run us through this to give us an explanation. So once again, logistic regression is a statistical method. It's used for classification where the outcome can be one of two possible values. So that's what we mean by a binary outcome. And it predicts the probability of that binary outcome. So it could be either yes or no, it could be one or zero, it could be true or false. So it works by fitting that S-shaped curve. So that S-shaped curve, of course, that is the sigmoid function or the logistic function, which we will look at shortly. So logistic regression will model probability. Basically, it is trying to predict the probability that given the inputs, the independent values of X, right? The probability that the outcome is going to be either of the two possible values, right? So it's going to give you a probability function. It's not actually telling you it is true or false, or it is one or zero, but it's telling you that the probability of it being true is 0.9 or 0.99. So the higher the probability, the more likely it is that it is that. And the lower the probability, the more likely that it is zero or false. Okay. So it models probability, it uses an S-shaped curve. Okay. And of course, the third thing is that it classifies the outcome. So this is what we mean when we say classification. A classification task is basically a task where you are going to classify the probability into one of two discrete categories, right? Like we have said. So once the probability is greater than that threshold, which is 0.5, then classify it as the positive outcome, yes or one or true. And if it is below 0.5, we classify it as the negative outcome, which is zero or no or false. So logistic regression function is made up of two components and basically a function of a function. So you have the linear part of it, which is a multivariable linear equation. We had already looked at multivariable linear equation. And when you are looking at multivariable linear equation, you have to understand that you are working with multiple variables. So you have multiple parameters, right? And then when you calculate the linear predictor, the Z, so in linear regression, this would have been a Y, this would be the actual outcome. But remember, in logistic regression, we are not trying to predict an actual value, but the probability of one of two states. So you then take the Z, which is the outcome from this, and you pass it into the sigmoid function or the logistic function. And it's going to give you that probability, which in this particular material, we will use the letter P to represent it. So this P of Y equals 1 or X is, this symbol means the probability that Y is true or 1, given a value of X, whatever that value of X will be. Okay, and that's sigma or sigmoid function of Z. And remember, Z is the linear combination of these um, this linear equation basically, which is a linear combination of the independent variables x1, x2, all the way to xn for any number of x's, right? So when you get that z, you pass it through this function, 1 over 1 plus e raised to the power minus z. So we talked about the sigmoid or logistic function. Sigmoid, it comes from the Greek letter sigma. It converts numbers into a linear, converts numbers on a linear continuous scale into a logistic classification or probability of a probability that is used for logistic classification, which based on the probability and the threshold, you can classify it either as 1 or 0, true or false, and so on. So it's made up with the exponential function e raised to power z, which is the original exponent function, right? Then that original exponent function, you flip it around and do some mathematical transformations. So the first flip is to flip it around the x-axis, around the y-axis horizontally. So you put a minus sign instead of y equals ex, which is the exponential equation, which you will see here. This is the y equals ex, the exponential equation. It looks like this. Then this is y equals e raised to power minus x. So when you reverse that, or e raised to power minus z, whichever one, and you get, it reverses this way. Then you can also flip it around this by adding 1 plus it and then inverting it. So you now get it going up this way. But it also ends up having a tail like this, which also the tail basically becomes 0, right? It tends to 0 when in the negative infinity direction, and it tends to 1 in the positive infinity direction. So what it means is it can never be higher than 1, and it can never be less than 0. So with that, you have effectively constrained the outcome between those two extremes, the 0 and 1. And it will never actually be exactly 0 nor exactly 1. It will be 0 at negative infinity, which is a very large number you will never reach. And it will be positive at positive infinity, which also will be a very large number you will never reach. So the sigmoid function becomes a very useful function for transforming the values in a continuous space into the values in a logistic space, which is a space of classification, right? So here I basically just tried to demonstrate that. So if you look at this, you actually see all of this was just me trying to plot this so that you can see how it looks, and that's it. This is not really code that we use for anything, but you will see that the nature of the function is always going to be like this, 1 over bracket open 1 plus np dot exponent minus x. So one other thing to mention is it is good to know that this point of inflection here, right? Like we said, if you draw a line of at position 0.5, right? That line is the threshold that you use to classify or differentiate between values that you will classify as the positive, right? Which are values on the above this line, right? And values that you classify as negative, or as 0. So values you could classify as 1 are above this line, and values you classify as 0 will be below this line, right? Now, I already mentioned that there is, of course, this this transition section that you will see where even though the x, the y value is not exactly close to 1 or close to 0, but it's transitioning, right? So of course, this threshold or point normally would be at a value of x being equal to 0, right? Or the value of z being equal to 0. But sometimes you can apply a left or right shift, right? Which I'm not going to go into that for now. So that's a logistic function, right? And that's how it looks like. Now, so the interesting thing is that this transition section, we can make it steeper so that we have a faster transition. And a simple way to make it steeper is basically to add a coefficient to the value of z, the independent variable. So we add a coefficient here, right? Basically, this coefficient c. So it becomes a multiplier to the independent variable that determines the y. And the higher that variable is, the steeper this place will be. So if you even look at what we have here at this point now, we have a value of c being equals to 2. So if you look at it, right, 2, you see it's not that steep. 1 is, yeah, the same thing as not having the coefficient at all, right? So you will see it's there, this is 1. But if we decide to make it more, right, maybe a large value like 100, then you will see that it is going to, it's going to be very sharp. 1 is a normal value. You can see 1 is very gradual. 100 is a very sharp value. Almost a step change. 1000 is going to be an even sharper value. So yeah, and we're even already getting an overflow there. So that is, but in most cases, you don't really need to do this. So you just run with the standard formulation. So now that we have the logistic function, which is the sigmoid, right? The logistic regression will use the sigmoid applied onto the linear combination of the x's. So you have pi, which is a probability. This is the logistic value, the predicted value, or the probability is sigma, which is sigmoid function of W transpose or omega transpose. So the omega or theta, sometimes you see theta being used here. That refers to the combination of all the parameters, what we were calling M1, M2, M3, and so on, right? All of them are bunched into one, which you can call either omega or theta, and you multiply it by xi. So xi is the value of x for each data point. So in this case, the I subscript here is used to refer to a sample or data point, right? At some point, I will kind of try to disambiguate because there are two series of data that we have to be aware of. But at this point, the cost function is what we call the negative log likelihood function or the binary cross entropy equation. So basically, I have explained this already. It just takes the log of the probability. And remember that the log of 1, if the highest, remember the highest probability is going to be 1 and the lowest probability is going to be 0. So the log of 0, which is the highest probability, is, sorry, the log of 1, which is the highest probability, is 0. And the log of 0, which is the lower probability or the lowest probability, is minus infinity. So that's a very high negative number. So what this means is that you have to apply a negative sign in order for you to be able to get the cost function, because the cost function is supposed to rise as the value rises away from what we want it to predict. So what we are looking at here is a situation where we are saying, if you look at this logistic curve and the actual value is true, and the predicted value is a probability, which is, instead of 1, it is maybe 0.5. 0.5 is very far from 1. So if you take the log of 0.5, that is a very negative value, right? So we negate it and we're going to get a very high positive value, right? So that is a measure of how far away 0.5 is from 1. Now, if the number is even higher, maybe instead of 0.5 is 0.25, right? It is even more negative. So when you apply a negative sign to it, it's more positive. So it also reflects the fact that 0.25 is much further away from the value of 1 than 0.5 is. Because what we are doing effectively is, um, let me just add a little bit of code here. So if you do a log of 0.5, let's do a log of 0.5, and then we'll do a log of 0.25. So, so you will see that the log of 0.5 is minus 0.69. The log of 0.25 is minus 1.38. So which one has a higher absolute value is 0.25. But in terms of, if we were just taking only the actual log without negating it, it will appear as if this one, this minus 1.38 is smaller in value, because a a high negative number is smaller in value than a low negative number. So that's not what we want. We actually want the 25, the one that corresponds to 25, to be a higher value, right? Because 25, 0.25 is further away from 1. Of course, let me just graphically represent it here. The distance of 0.25 from 1 is this, which is short, but the distance of 0.25 is much more. So if we negate it, you now see that negating it actually makes more sense. It reflects the relative distances away from 1. So you now see that 0.5 that has a higher value, right? 0.5 that has is closer to 1 will have a lower value, while 0.25 that is further away from 1 will have a higher value. So that means that the log function, the negative log function, is a good way of um, calculating the cost function in this case, because what it means is that we don't really care about actual values, but just how far away it is from this. So that is, but that is only if we want to predict 1. Okay, like I said, if my y is 1, if I want to predict 1, it makes sense if the actual value is 1, right? If the actual value is 1, then I want to predict 1. So if instead of predicting 1, I predict 0.5, I am closer to the right answer than if I predicted 0.25. Okay. But what if I want to predict 0? If I want to predict 0, if the actual value is 0, that means I want to predict 0. Then you now find that if I still do if I do logs, right? By the way, somebody could say, okay, let's just do logs without the signs, right? Let's do logs without the signs. Well, that might work, because if I want to predict 0, in this case, when I'm predicting 0, the value, if I'm predicting 0 now, so we're talking about 0.5 and 0.25. If I'm predicting 0.25 is closer to 0. So the cost for predicting 0.25, if the true value is 0 and I want to predict 0, the cost is lower. In other words, if I predict 0.25 instead of 0, it is a lower cost than if I predict 0.5 instead of 0. So we want to have a higher cost, right? We want a function that will give us a higher value for the cost of 0.5, right, than 0.25 if the actual value is 0. Now we could just use this as it is, but we'll end up with negative values. So that's the other reason why just using an ordinary log is not a good idea. You end up with negative values, which is not very good for measuring cost. And the fact that if I want to combine costs, right, that means that when I'm doing 0 and I'm doing 1, I'll be having negative values um, when I'm predicting zeros, and I get um, higher value than 0. I'll get negative and then I'll get positive. So they'll tend to cancel out. So we'll end up having to do square and all of that. So that doesn't really make sense because that's extra computation, which you don't need. So the best option is, yeah, let's still go with the um, negative sign, right? But because probability, right, is the probability is always sum to 1, right? So that's where the, logic came from. Okay, probability sum to 1. So if probability sum to 1, then why don't I just do the probability of the opposite? So I flip it. So if I want to predict 0, let me first of all subtract the actual value that was predicted from 1. And then what is left will be a measure of how far away. So it's basically the same thing as what we were doing with 1, except that we are flipping it. So with this, you're now going to see that the probability of me predicting the cost of me predicting 0.5 when I should be predicting 0 is the same. You can see 0.69. It's exactly the same as the cost of me predicting 0.5 if I wanted to predict 1. Of course, that is correct because you are right there in the middle, right? So if the cost is a measure of the distance from what I want to predict minus what I'm actually predicting, then it is a good measure of it, right? Which is really what the cost or the loss. The loss is the difference or the distance between what I am predicting and the real value. So if I'm predicting 1 and sorry, if the real value is 1 and I'm predicting 0.5, right? The cost should be equal to if I want to predict 0, but I'm actually predicting 0.5. But conversely, um, if I am predicting if the actual value is 1 and I am predicting 0.25, right? Then this distance, right, like we saw before, is 1.38, right? So if on the other hand, I am, you know, the true value is 0 false, but I end up predicting 0.75, right? Then it should be the same as the converse, which is me predicting 0.25 when the true value is 1. So in other words, this arrow here, right, and this arrow should be the same length because they are basically the same measure of distance from the actual value or cost. So that is what makes this a very good measure. You basically use what we call is the mathematical converse, is the converse of it. We always say in probability, this is all based on probability theory. If the probability of something happening is n, the probability of that same thing not happening is 1 minus n. The probability of something happening is p. Probability of that thing not happening is 1 minus p. And it's as simple as that. So that is how these two pieces of the equation, was arrived at. So effectively, negative log likelihood is a combination of two piecewise equations, right? When we say piecewise equation, well, it's actually one piecewise equation that is made up of two parts. The first part is when the actual value is 0. Sorry, when the actual value is 1. I want to predict 1, right? So I'll use minus ln p, right? And when the actual value is 0, I want to predict 0. So I use minus ln 1 minus p. This is just based on probability theory. So now we combine these two, but the way to combine it is to ensure that if I want to predict 1, then this particular term in the combined error or loss should diminish or be eliminated. So how we do that is by using 1 minus the value that I actually want to predict. Simple. This is very intelligent way of thinking about it, right? So if I want to predict 1, then 1 minus 1 is 0, right? So this is 0. And 0 times anything else is 0. So with that, I cancel out this part. So the piecewise equation now uses just this part, right? So this is for when I want to predict y as 1, when y, the actual value is 1. But when I want to predict y as 0, the actual value is 0. Then this same equation works in that case as well, because if y is 0, then this is 0, right? And 0 times anything is 0. So that eliminates this piece of the equation. And what you'll be left is 1 minus y, which is 1. So by the way, this is also 1, right? So you can even just take it away, and what you'll be left is this one, because 1 times anything is 1, you know. So with that, we are sure that when the actual value is 1, I will be using this one as the cost function and or the loss. But when the actual value is 0, I'll be using this term as the loss. So with that, you have this combined error or loss function for logistic regression that takes care of both situations. And that is the basis of the cross entropy. This is what we call cross entropy. And that terminology comes from that cross, cross pollination, kind of when this one is 1, the other one goes off, right? So it's the interaction, the cross interaction between the two terms. So you take this cross entropy loss function, and of course you do the normal thing. The loss function is the loss for a single data point. You now sum it across all the data points, which is 1 to n, right? You divide it by n, and that gives you the average. And of course, you apply the minus sign. So remember what we said, this minus sign starts from here. You have to negate the log, otherwise you get negative numbers. So with that, that gives us the full equation for a logistic regression, the full cost function equation, which is the NLL, negative log likelihood. And that's it, right? So again, remember the P is the probability. Now there's some new notation here which I want to explain. So the first thing you will notice is that we have two sets of subscripts. You have a subscript I up here, right? So the I, going forward in our own terminology, we'll use the I subscript in bracket, or I superscript rather, in bracket. We'll use it to represent the data point. So I in bracket superscript means the ith data point. In other words, the ith sample. Okay. While if we use I as a subscript, that will refer to the feature, or J or K, whatever. But if it is a subscript, it refers to the feature. So like this one, M2, X2, this is one feature, right? Or one independent variable, right? Then you have M1, X1, that's also one other feature. That's another independent variable, and so on. So you actually have N possible combinations, or have N possible features that are combined together plus the single bias constant that you see here. So these subscripts are different from this. When we get to vectorization, I'll explain that a bit more clearly. So that is the derivation of the logistic regression cost function. And this is how you can see it. When we are talking about, an expanded form of it, right? For a single data point, first of all, of course, this is a sigmoid function, like I have said. If we have 3 independent variables, right, you will now see that for each data point, the value of the y is going to be m1 times x1, which is the first term or first feature, plus m2 times x2, which is the second feature or second term, which is made up of the independent variable itself, x2, and the parameter that controls it, or the coefficient, which is m2. And then you have m3 times x3, which is the third term. And then you have c, which is a constant term, right? So this is the predicted value. So now the you have what we call the error, right? So the error is basically going to be the prediction, right? When for the y0 in this case is the first data point. So each data point will have its own separate error. So this underscore 0 kind of represents the I subscript, I superscript in bracket. So what that means effectively is that the error for each data point is the y0 or y for that data point, which is the prediction for that data point, times the log of the prediction for that data point, plus 1 minus the actual value for that data point, times the log of 1 minus the prediction for that data point. As simple as that. And so you do this for each data point. So for the total error, you get the sum. So this is a programmatic way of writing the code that will give you the same thing as this summation here. Now, there's something I missed here. This is actually sum over n, right? It is a sum over n. And there should be a negation, a negative sign there. So it is minus mean, right? It's minus mean, not sum. So I'll correct that. In fact, let me correct that right now, because this is actually minus times the mean. Each of the errors actually has a sign as well. So yeah. Okay, so this is just the way of writing it in code. So I tried to do a bit of visualization just to help us understand. This is the p probability function, the log p, right? This is a minus log p, and this is the um this is the minus log 1 minus p. So this is the minus log p, which is the this is what you use when I want to predict one. So what that means is that when I am predicting, if the prediction is 1, the error is very low. But if the prediction is 0, here, error is very high. So that's what you use in that situation. But this is the converse when you want to predict 0. So if the value I'm predicting is 0, then the error is also 0. But if the value I'm predicting is 1, then the error is very high. So those two. So by combining those two, if I were to do the full negative log likelihood, you would see it is an interesting curve as well. But this is how you combine those two. So that is where we got to, right? Now, for the gradient is actually a very simple form, right? When you do the calculus of it, you find that at the end of the day, the gradient is basically just the difference between the predicted value and the actual value. That's what it is, right? This p minus y is what we call it's yeah, it's the difference between the predicted and the actual value, right? So that is the total error. That's the total error in the system, right? Then for each data point, or for each feature, right? For each feature, you will then take this and multiply. So just this is basically the same exact equation as what we use for linear regression, right? Because with linear regression, what you do is that you calculate the difference between the y is typically y minus y pred, right? Or y pred minus y, whichever one you choose. But as of course, remember, I take note of the sign as you are choosing which one of those two. right? So if you do y minus y print, for example, that is the error. You then take that and multiply by the value of x. That will give you the gradient for just that x, right? The contribution of that x to the entire error. And then you take the average for all the x's, right? You take the average for all the x's. So so this is the gradient for logistic equation. So again, so this is now looking at it from this is the formalization of that equation, right? The del, or the partial derivative of the negative log likelihood with respect to each weight, right? Wj is each parameter or each feature or each term, right? Is going to be for each data point, right? Remember the I at the top is the superscript, is the data point. So for each data point is going to be p minus y for that data point times the x value of that feature in that data point. So you can see it's kind of a two-dimensional calculus there. So that's what I just said. Yi is a true binary label for the ith example or sample or data point. That's what I call data point, right? And then the xji is the value of the jth feature. So if you have three features, it's going to be x1, x2, and x3, right? Plus a c, okay? And so on. For the ith example, so for each example, you will have a gradient for each of the contributions, okay? And again, remember the probability is predicted using the sigmoid function, which is 1 over 1 plus e raised to power minus w dot x. So it's interesting to see that this w dot x is the same thing as z, right? W dot z is the combination, the linear combination of the different features. So for the entire data set, right? For you to get the full gradient of the entire data set, still using the same formula, right? This is now breaking it down so that we can see. This looks like it's a lot of stuff, so it might be a bit scary, right? But it's not that scary if you really look at it. If you look at it, you will see that this is the partial contribution of M1. Remember, we're still using M1, M2, M3, and C, just to correlate it what we have before. So it's easy for you to move from the multi-variable linear regression to a multi-variable logistic regression. So you can still be able to, keep everything in your mind and change a few things. The only main difference between multivariable linear regression and multivariable logistic regression is the sigma function. That's the first difference that you use to change the way your output gets mapped to probabilities. The second is you are using negative log likelihood to calculate your cost function. Those are the only two differences. But the gradient is calculated exactly the same way. And this is a calculation. It's going to be p minus y, which is saying y hat minus y, basically, right? Times x for these data points times x1, right? And then you now have p minus y. Remember, we are calculating the contribution of gradient m1. So it has to be summing up all the contributions of x1 for all the data points. So the first data point, which has this superscript of 0, right? You multiply it by x10. You add it to the error contributed by this p minus y again, y hat minus y, basically, times the x1 of the next data point. So again, remember what has changed is this upper subscript, or sorry, this upper superscript, this superscript here. So this superscript is for the second data point. This is for the third data point. So if I were to kind of draw squares around them, right? This is data point 1 contributing this error to it. This is data point 2 contributing this error to it, and so on, all the way to the nth data point, right? all the way to the nth data point. So all of this each contribute an amount of error to M1. And that's why you are doing this. Then, of course, you divide by n, so you are taking the mean. The same thing for M2. You also calculate the total sum of contributions of each of them and multiply by x2. So y hat minus y, right, times x2 for this data point, y for the 0th data point. Then for the first data point, again, y hat minus y times x2. For the third data point, again, y hat minus y times x2, right? And all the way to the last data point, which is end data points. Again, y hat minus y times x2. And you do this for all of them. So whatever number of parameters that you have, this part of it, you do it to match the number of parameters that you have, right? That's the most important thing you do. So if you have 3 parameters, you do this 3 times. If you have 4 parameters, like we have in this case, where the fourth one is a bias, you do it this way. And you just keep going that way until you have calculated all of the contributions, right? And that's just it. Then, of course, when you get to the constant, for the constant, there's no multiplication because there's no influence of x. There's no x next to a constant, right? So the change to the constant will be just the sum of each of the errors in each of the data points, right? Across, sum it, and then divide it by n. So it's going to be the mean. And this is just a simple principle. If you think about it very well, this is the same thing that you were doing when we were doing um, multiple variable linear regression. So it's just the same thing. The only thing that has changed is that we are now using P instead of saying Y hat, but it's basically the same thing. And the reason why we're using P is because with Y hat, we're using a linear equation, right? But with P, we are using a logistic equation, okay? Okay, so are there any questions so far? So to now do the logistic regression, right? Um, you it's easy when you're writing code to make your code cleaner for you to write each gradient. So for each data point, you calculate the gradient, which is y pred minus y0, which is p minus y0, right? Which is y hat minus y0, all the same thing, right? So for each sample point, you calculate it separately. And then you can now take each of those gradients and combine with the x's, that the corresponding x's, and you sum for the DM1 grad 0 times x1 when for the data point 0, plus grad 1 times x1 for data point 1, and so on all the way to the nth data point. Same thing with DM2, it will now be x2 for each of those data points. And then for DM3 to be x3 for each of those data points. And for C, it will just be grad 0 plus grad 1 for all of the data points, right? That's it. So when you sum all of that together, that gives you the gradient. And once you get the gradient for each of the coefficients or each of the parameters or each of the peters or whatever, all terminology is basically pointing the same thing. You can then do the usual gradient descent. Once you get the gradient, you do the gradient descent, which is decrease that parameter by that gradient times the learning rate. So it's as simple as that. So with that, we will now do a simple example. So if you look at this example, right, we have 2 parameters, right? 2 independent variables, right? And that is x1 and x2, just like what we did before. You have x1 and x2. And this is just a way of extracting those variables or those values, rather, the x1 and x2 values, right? And the y values from this list here. So this is a list of numbers that is in a string format. So this is just another way of extracting data. So we end up with x and y. So x is a 2-column, 2-dimensional matrix, basically. And then y is a 1-column vector. So this is the input data we want to predict. So the first thing we do, which I think I made a bunch of comments like that for some people, but one good way for you to measure, um, how close your prediction, especially for multi-dimensional, multivariable prediction, is to just calculate the predicted value of y and plot it against the actual value of y. So here, what we did was we actually plotted x versus y, right, to see how it goes, right? But we don't have any model yet, so we're not plotting that one yet. But here we are just plotting x and y values. And you see you have two series. You have the red series and the blue series. So the red series are basically the first, the blue series are the first value of x, and the red series are the second value of x. Yeah, so now we now go on to the implementation. So of course, you start first by defining your sigmoid function, which is 1 divided by 1 plus exponent of minus z, z being the independent variable you're passing in, or the combination of the um, independent variables, right, in a linear equation. Then, as usual, you get your three parameters, m0, m1, m2, right? Then we get an alpha of 0.1, 0.01, which is a good alpha to use as the learning rate. It's a good value to use for simple regression problems. Then we choose 100,000 epochs. 100,000 epochs is when you start doing, when you're doing simple linear regression with a single variable, you find that 100 epochs is enough, or 100 cycles, or maybe even 500, right? At most 1,000. But when you start doing this more complex stuff, right, there's this trade-off that you have to do between your learning rate and your number of epochs. You converge faster if your learning rate is higher, so you need less epochs, right? But you also run the risk of exploding gradients and then just diverging instead of converging. So what you do in that situation is you reduce the learning rate so that you don't have exploding gradients. But when you reduce learning rate, you have to compensate by increasing the number of iterations or number of epochs. Otherwise, you will not get optimal point. I noticed when I was grading tasks, a lot of people were using inadequate number of epochs or learning rate that was too low. So they never really got there. So one of the things I want to let everyone know that in this class, it's not just enough that you can demonstrate and show the, the equation or the loop. You actually need to train the model and have it have good KPIs. It should be able to predict properly. So it's not just enough, oh, here's a formula and this is how you know. It's not just about the theory of it, right? It's not about the theory. It's not an academic exercise, right? Rather, it is a practical, we are trying to actually train models that can be used in the real world. So I want to start at this point as early as now to tell you, ensure that your models converge and get to the lowest optimum possible so that they can predict correctly, okay? So you have to be very careful the values of the hyperparameters you pick. And these are two of the more important ones, right? The epochs, which is the number of training iterations, and the alpha, which is the learning rate. And these two are always related, right? The third thing that also matters in this relationship is the gradient. If your gradients are huge, are large, you want to go to a much lower learning rate. But if your gradients are small, you want to go to a higher learning rate. Okay? So what that does is, so I'm giving you the tips so that you know that there is be thinking about it, right? Gradients and alpha are, they go in opposite directions, right? Gradient and alpha. But gradient and epochs go in the same direction. So what that means is if you increase the gradient, you have to reduce the epochs, right? for the same thing. But if you decrease the if you increase the learning rate, the alpha, you have to decrease the epochs, right? But if you decrease the learning rate, you have to increase. Oh, sorry. Let me back up. They go in the same direction. If you reduce the learning rate, if you reduce the learning rate, you have to increase the number of iterations. If you increase the learning rate, you have to decrease the number of iterations. If the gradient is higher, you have to reduce the learning rate to reduce the chances of exploding gradients. But if the gradient is very low, you have to go with a higher learning rate. Otherwise, you will never converge. So those are kind of the interrelationships between those hyperparameters. Okay, so having done this, right? So we have the data, right? Let's start here. Import pandas. So we get the data. We plot. So this is kind of a preparatory or exploratory data analysis just for you to look at your data and see how it looks like. We are going to go more in depth into this next week when we are going into feature engineering and data preparation. So we know the correct way to prepare data before you plug it into your training pipeline. So far, what I had done was give you data that's already been prepared or doesn't need much preparation that you just plug into the training pipeline. So this is the sigmoid function. These are the hyperparameters and the training and the parameters, right? Then you do a little bit of visualization of the data. So here is me doing just a single prediction to see how it looks like. So we do a single prediction, which is the sigmoid times the linear combination of the parameters. And then I use the negative log likelihood, right, to calculate the cost, which is minus y. So this time we're using let me use a term, half vectorized format. It's not fully vectorized, right? It's vectorized, it's column format. So this y refers to all the data points. So I don't need to go through a loop of y upper superscripts, I kind of thing, right? So I take all the y's and then I multiply by log of the predicted y, right? And then I add that to 1 minus y and I multiply by log of 1 minus predicted y. So this gives me the cost. This is going to give me the cost for each of the data points, right? Each of the data points. Then we now subtract from that, or we subtract that from the predicted y, right? We subtract y from the predicted y, okay? That is what we call a residual. There are different kinds of residual, right? So, but what we call the raw residual is basically just the difference between the predicted value and the actual value. And that's what I was saying, that distance between predicted value and actual value is a measure of your cost, right? So it is called the raw residual. So the next thing we do is, based on this, we can now calculate the gradients for each parameter. So if I were to, let me run this, right? So that you can see what is going on. Okay, there's something I should do here so that we can see. Okay, I've put everything in a data frame. So the this DM0 is the gradient for each parameter, right? Sorry, the gradient for each data point for this particular parameter, right? That's DMO. DM1 is a gradient. By the way, the MO is a constant factor, which we were calling C before. I am now calling it M0, right? We're calling it C. I'm getting us gradually to the point where we'll combine all of these things into a single huge matrix. We are going towards full vectorization now. But now we are kind of doing half vectorization, if I may use that terminology. So the DM0, you see this column here, that is DM0. So DM0 is the list of gradients for each data point, right? With respect to the constant factor C or M0, that parameter. DM1, you now take the raw residual and you multiply by each value of X or X1 in this case, each value of X1, because this is just taking X1. The first column of the entire X is X1. So you multiply the raw residual by that. That will give you the gradient, right? For each, for the value of X1 or for the value of M1, which is the coefficient of X1 for each data point, okay? And then DM2, the same thing, but these are around for the second coefficient, that is the coefficient of X2. So, so I hope you are hearing me clearly. I can see a couple of mentions of network, so I hope I'm being heard. Give me a thumbs up if it is okay now. So with this now, you can see that I am now doing a data frame to combine all of this just for us to see how these values look like. So the first column is all the predicted values of Y for each data point, right? We actually have, I think we had about 20 data points, right? I didn't check the shape, but it's something you can easily check. Um, Let me do that quickly here, right? So yeah, there are 50 data points, right? So for X has two columns, right? While Y has one column because it's a single vector. So for these 50 data points, I just printed only 10, right? But if I had printed all, okay, if I had printed all, you would see all of them. So there are actually 50 data points. So the Y pred is the predicted value for each of these, and then the Y is the actual value. So you can see, like in this first one, the actual value of Y is 0, meaning, false. But the predicted value, well, the predicted value is actually quite low. So you can say it's close to 0. So it's not bad. Here, the predicted value is 0.02. It's still far from this, but it's quite close. It's not that far. While for this one, the predicted value is 0.99968183, 0.99. Yeah, well, this is because I guess I have already trained this model, so it's getting pretty close. Let's start all over again. So you see the original values. You can see from the original values, they were not very good. They were actually not very close. So anyway, these are the predicted values, and these are the actual values of Y. So you can see the 0 and 1, which is the label. Then the cost. So you will see that for this one, the cost, because it's 0, we are using the second part of the piecewise cross entropy, binary cross entropy equation, and it's just giving me this same value, right? This is log of 1 minus this, so it's this. So, but you will see that the ones that are close to 0 will have low values. This one that is 0.61 is far from 0 is going to have a high value, right? Then 0.77 is close to 1, right? So it has a low value. But 0.62 is far from 1, which is a predicted value. So it has a higher value. 0.39 is close to 0, but it's not that close. So this allows you to really see and visualize that negative log likelihood function, how it behaves for different values of Y and different values of Y pred. And then these are the different gradients that have been calculated. So you see that for each parameter, there is a list of numbers that correspond to each data point. That is a gradient with respect to that data point. So you have DM0, DM1, DM2. So I just ran one iteration of this, right? Just to get these values. Then we do a plot. So this plot is always very interesting, and it's a plot I would encourage a lot of people to do, right? If you are training, this plot gives you an idea of how well your model is able to predict. So you can see that here is where you have the higher values, right? This is the other end. This is the positive end of the y value, right? Of the two possible values, and this is the negative end, right? Or the falsy end. So now the correct positioning, or the correct way this should be, is that everything that you predict should be here or here. Essentially where you have those red dots. Because it means that when it is true, sorry, when it is false, I should predict 0 all the time. And when it is true, I should predict 1 all the time. So any value that falls outside of this range, like these ones, are erroneous. Of course, again, let me rerun this because I've actually, I'm running a trained model. So this is the original model. So you can see the drift, right? You can see the drift. This is a very clear measure of how poorly this model is not predicting well at all. And why do I say so? Because if I draw a line across this center point, remember we said this point 0.5, that is the threshold. That is where you that's the value that you use to classify and basically separate between the truthy values and the falsy values, right? So the truthy values are doing quite well anyway. Most of them are above the line, which is where they are supposed to be, right? But the falsy values are not doing well at all, because you can see that a lot of the values, the false values, have gone across this threshold point. So this is where true values should be, and false values should be below this line. Well, you now see that there's a whole bunch of false values that are above the line, right? That's not where they're supposed to be. So all of these values will give you a very high cost score, a very high loss value, because these are far away from the 0. So they will get a high score, right? But even these ones that look like, oh, they are looking good, right? They're not really that good, right? Because as it is, they are still sufficiently far away that they will not make a good prediction. Okay. Even these ones too are, so far away, they will not make a good prediction. So when we train, one of the parameters, one of the things you look at to know, have I reached optimal point? Should I stop training, or this number of epochs, is it enough? Should be how much in this kind of logistic regression problem, how much are these numbers bunched around here? If the numbers are bunched around these points and these points, all of them or most of them, then you have got it right. But once you start having them stray out this way, right, it means you're not there yet. So you have to keep training. Okay, so that is basically what we use this plot for. So this plot is simply a plot of the y versus y pred. It's a plot of the actual value against the predicted value. And then you can also do a scatter plot of the actual value against itself with a different color. That shows you the reference, what is actually supposed to be. Okay. So with that, now we run the training. So you can see I have done this. I had already picked the number of epochs, and I had picked 100,000, right? Learning rate is pretty okay at 0.01 because I don't have very high values, right? So we trained for 100,000 epochs, and this is now what it looks like. So you can now see that here, the values have started plumping into this, even though you still have these other guys that are kind of outside, you know. So for me, this training is not yet converged. It's not yet fully done because of these two outliers, that are apart. Particularly, there is this one point that is so stubborn. It continues to remain at 0.5. So it's even very likely that this can get classified as a truthy value, right? It is falsy. That is, it is supposed to be zero, but it's so close to 0.5, you know, I think it's slightly below 0.5 though, but it's so close to 0.5. I could see that it could be miscategorized. Okay. This second chart is just a plot of the loss values or the cost values, right? Over time, as you continue to train, it drops. And you can already see this asymptotic behavior where it is basically not, getting any closer to zero. Of course, you will never get to zero, right? It gets to a very low value. And you can actually check what that low value is because we had the parameters printed out. I always ask, so you see the cost here is 0.0365. We can try to train further and see how well it will do. So I could actually run this. Let me run it for another 100 epochs. And let's see, 100,000 rather. And we'll see where it lands us. So you can now see we have this at 0.02. So these are getting closer, but this friend is still hanging. You can see it's actually coming closer, but it was in between here, but now it's coming closer. If I run it for another 100,000. So at this point, I'm going to show you something like, let's say you can see it's getting closer. I now want to train this model to really converge. I want this single dots that is here to come all the way down. So what do? I will train it for maybe 10 million epochs. Now that's a problem. How can I train for this number of epochs? How many? It will take years, right? But the good news is that Colab actually gives us access to a few GPUs. So a GPU is a graphical processing unit or a graphics processing unit. Basically, to cut the long story short, I introduced it when I introduced machine learning generally, but it allows us to be able to run all this training much faster. It is much faster, like 10 to 100 times to 1,000 times using a CPU. You can switch to a GPU here by clicking on this here, right? This arrow next to the runtime selection. You have RAM. This is a show of your metrics, how much capacity you are taking. So system RAM, this is what I'm consuming. Disk, this is what I'm consuming. Now, I can click on this and I can choose connect to a hosted runtime. Okay, that is connecting to the CPU by default. I want to choose which runtime. So I'm going to select the second option, which says change runtime type. So if I click this, you will see this dialog that allows me to choose. So these are three main things that make up the runtime. The version of Python you are running. You can also use R or Julia, right? Which is quite interesting. Then the runtime version, which in this case, the version of Python, but you can always go with the latest, which is recommended. And then the third thing is the hardware that is running this thing, what we call the hardware accelerator. If you pay some, cash, you can actually get some really good compute. But right now, Google gives us T4. It gives us a T4 GPU and it gives us a V5E1 TPU. A TPU is what we call, Google calls it a tensor processing unit. It's just Google's own specialized brand of compute, right? That basically does the same thing that GPUs do, but much better, according to Google. So that's a TPU, right? A tensor processing unit. A GPU is a graphical processing unit. So you can use any of these, right? Now, let's do a little bit of stuff just to show you how much better GPUs are than a regular CPU. We are going to run some timing. So we're going to run some timing to measure speed of compute, right? This is just an aside, right? But it's good to um it's good to be able to do some of this sometimes, right? So um you can just do start equals time dot time, right? Then when you are done, maybe before plotting, because I don't want to include um the printing time as part of the compute time. So before then, you can just say end equals time dot time. And then you just print the time taken and see how that will give you in seconds. Now I'm going to change this epochs to 1 million, right? What we have is 100,000 now, 1 million. Now this becomes much more difficult to read. So sometimes in Python, you can use underscore to separate the digits, okay? So this is 1 million. And I'm going to just run all of this again. I'm still using a CPU, mind you. So if I go to, I'm still using the CPU. So I just want to, so 1 million, you can see this is still running. And it's going to take a bit of time. Probably will take up to maybe a minute or so. We will see how long it takes. By the way, this time will measure time in seconds. If you need more, um, if you need more granular time, like more precise timing, you can use time dot get time in milliseconds or millisecond time, right? That'll give you time in milliseconds. So this is running. I'll just wait for it a bit. If we had commercial now, I would have said, okay, let's take a commercial break. All right, so it's done. Okay, so look at the time taken. It takes 57 seconds. But I now have cost none. So I have run it so much, we're now having what we call vanishing gradients. Can you see now? The cost is probably so low, right? There's something we call vanishing gradients. This is the opposite of exploding gradients. Vanishing gradients when the gradients are so small that it actually underflows, what we call a numeric underflow. The number is so small that the computer cannot represent it anymore. So, but typically numeric underflows will show as 0, right? But here it's a none, okay? So it's giving me a cost of none. But yeah, so we have this has come close, really close. You can see it's now at 0.2. And this is really like probably the best we can ever get. Maybe if we go for a lower at some point you switch to a lower learning rate, we may still be able to push it down without causing nans. Okay. Now, the main thing I want to show us here is that we've taken 57 seconds using a CPU. Let's run the same thing now by changing runtime type and use a T4 GPU, right? I'm going to have to delete the old runtime and then click on save. Okay. Then I'm going to rerun this. Once it's connecting now, once it has connected, hopefully I can easily get one. It's connected. I can now run again. And then let's see how long this takes. 57 seconds on a CPU, right? 57 seconds on a CPU. Let's see how much a GPU, what GPU was that now? This is a T4 GPU. T4 is not really like, it's a really old type. You have the A100s, which are much better. You have L4s. You have Broadwells, these are really old. That's why they're kind of, it's available to us because modern GPUs are really difficult to find, right? Yes, it will cause overfitting. No, it will not cause overfitting if you manage your learning rate. So you only cause overfitting. Well, overfitting will always happen when overfitting does not come from training a model for too long. right? Overfitting comes from um, building a model that is too large for the data. Well, this time it takes 53 seconds, which is interesting. I was expecting much lower numbers. So let's try this other one, which is the let's change it to a TPU. So overfitting, you don't get overfitting by overtraining, right? Unless you're well, you will get if your learning rate, if you don't condition your learning rate very well, right? You get overfitting when your model is bigger than the data, or when your data is too small. But when you say your data is too small, it's not like data itself is too small, right? But the model also is bigger than data. And remember, the model, what one of the key parts that make up the model is the number of features. In other words, the number of X values, if it is too much more than the number of data points, then you end up overfitting. It's entirely possible that this thing is not really using any of those. Okay, so this is 31 seconds. It's an improvement. I was actually expecting like 3 to 5 seconds, but so if you want to speed up a bit, you can choose to use any of those. So with that, I think we are done with logistic regression. Any questions before I move on to the next thing, which I want to talk about? Vectorization. Any questions? Okay. So we have kind of done all this while we've been doing stuff with what I call partial vectorization. In other words, the data points are a vector, but the features are not a vector. We are still writing three different equations. You can see here, this is a good example. We are writing three different equations, right? For each parameter, the gradient of each parameter updates, right? But when we are calculating the cost function, we don't write out each data point, right? Each of the values of y. So this is kind of a vectorized y, but the x itself is not vectorized. We kind of split out the x, even though x itself is a matrix, so it's a complete vectorized thing, but we are still separating out just one column of x, the first column of x to use with M1, right? And then the second column of x to use with M2. So this is nice, but it's not fast, right? Vectorization is ultimately when everything, I use a single matrix operation to do this. And how do you do vectorization? So let's look at it this way. Vectorization is an approach for solving a system of linear equations, right? By converting them into a matrix product. So you're basically going to have a matrix product, either a dot product or a cross product, either an inner product or an outer product, right? So typically when you are solving linear or logistic regression with multiple variables, vectorization is the best approach to use, right? And it's a very important skill for you to have. So let's start with a simple vectorization in your case. Let's assume that we have three equations, right? In other words, three data points. Each equation represents a single data point, which we are trying to predict. These are three data points. So you can now see that we are still using the superscript, the number superscript in brackets. So we have three of them: data point 1, data point 2, data point 3, right? But for each of these data points, you have a linear equation, which is a combination of three um, independent variables, each of them with their own coefficient or parameter, and then the constant or the what we call intercept, right? So, or the bias, whichever one we want. So we combine this, right? Constant plus um, um, parameter 1 times x value 1 for this first data point, plus parameter 2 times x value 2 for the same data point, plus parameter 3 times x value 3 for the same data point. So you have, for the same data point, you combine three values of x, right? And the corresponding, but take note that the parameters are different, right? But you now have the second equation, which is basically a replica of the first equation, but for a second data point, a new data point. And so you have y2, this is data point 2, right? Superscript 2. So you see the same parameters, the same c, the same m1, the same m2, and the same m3, basically the same parameters, right? But you now have different set of x1, x2, x3, right? This is x1, x2, x3. Let me correct that. This is x1 and this is x1. So you have x1, right? But for the second data point goes with m1. And we have x2 for the second data point goes with m2. And then you have x3 for the second data point goes with m3, right? And then you have the third data point or the third sample or the third item in the sample. Again, you have a y value, y pred. Then you have c plus, again, m1, x1, but for the third, m2, x2 for the third, and m3, x3 for the third. So you see, this is a system of linear equations, right? So like I said, we represent each data point or item in a sample with a superscript number in brackets, right? While the subscript represents each independent variable or each feature. So this is now what we call feature. When you hear of a feature in machine learning, a feature means which each of the things that contribute to the outcome of the prediction or the outcome of the thing that you are predicting, right? So here you have three things. Actually, you have, well, okay, you have four, right? But this one is typically biased. It's not tied to an X value. It's not tied to an independent variable. So it's just a kind of, it's the intercept, because there's some kind of situations where without any independent variable, the thing that you're trying to predict still has a value, right? That is handled by this C. So each of these is a feature. So you now see that this is now a matrix of data points against features. The data points are on the row, are row-wise, arranged row-wise are the rows, while the features make up the columns. It's as simple as that. So we then extract this and rewrite it as a matrix, matrix and vectors. So that's what we now call a full vectorized form. So if for those who understand how matrices work, I'm not going to go into that. You can go study that. But you have the y1, y2, y3, right? Being equal to, you extract out the x's. And you can see that the C will be left, when you take out the C from this first column, right? What you get behind is the ones, right? And that C comes up at the top of this vector. Then when you take out all the M1s, which are, the M1 is basically you factorize it out. That is the first parameter. You take it out, what you'll be left will be the X1 for each data point, right? X11, X12, and X13. Same thing, when you take out the M2, which is the second parameter, right? You take it out, you'll be left with the X2, for each data point, X21, X22, X23. And then, of course, the M1 and M2 will come here. And then the final, last but not the least, you take out the M3s, right? Again, you factorize it out. Then you're going to have M3. This is a dot product. And for those of us who can do a bit of vector matrix multiplication mentally, you will see that if you multiply this matrix by this vector, you are going to get back this equation exactly as it is. So with this, you can rewrite this whole big vector of independent y values, independent data points, as a single big capital Y. So this is where you need to differentiate between a small letter y and a capital letter Y. The uppercase or capital letter Y represents a lot of data points. So this could be 100 data points, it could be 3 data points like we have here, it can be 20, it can be 100. So this is just a representation of it. And then the X is now a representation of all the values of X, right? And in this case, with the bias factor also added in as ones. So all of this X, so you don't need to even do it XW plus C anymore, like used to be done. By the way, you could actually have done this. So let me show you another way you could have done this, right? I did not do this here, but you could easily have done this way. By writing it as M1x1 plus M2x2 plus M3x3 plus C, right? You could have done that. And in doing that, you would have been able to basically separate, right? Separate the values of the C out, right? And then what you have is x1, x2, x3 times M1, M2, M3 plus, C. So that will still be XW plus C. So that's one way of doing it, right? But at the same time, you can just you know, bring the C out here and make the C into a parameter. And I think it's easier that way. Because when you are doing the gradient descent and everything, all of that, you don't need to have a special case for C. So in order for C to work here, you have to add this one so that when you multiply back, you get back the same thing. So with this, you can now see that the y is this vector of little y's, lots of different data points, is now equal to one big Y. And then this vector of x's with the one bias is also represented by a big X, right? And then the W, which represents the parameters, now is a vector of all of the parameters, including the constant factor, right? And these parameters or coefficients, sometimes you see in some places they call it theta. Theta is basically the the other way that it is represented. So you can either see that y equals x theta or y equals xw. So with that, that is how you vectorize. So this is vectorization now for a system of linear equations. So we can now use this general approach to now express how we would vectorize linear regression. So with this linear equation is y hat equals x theta. Now this is just another way of writing it. I started off writing y with, so let me change this because the convention typically is to use a small letter y to represent a vector, while an uppercase or capital letter Y to represent a matrix. So while I tend to prefer to use an uppercase Y whenever you have either a vector or a matrix. But then that would kind of break this this convention, because now the parameters I'm using a lower, so either way, right? The main thing is this is a vectorized form, right? Y or y hat equals x theta. So that's exactly the same thing we have here, except that we're now using y hat instead of y, and we're using theta instead of omega or w. The cost function is now written this way. So this is breaking it down, right? Again, into semi-vectorized form, right? But the vectorized form is 1 over 2n x theta, which is this, which is a y hat minus y. This thing is a double line, which means a norm squared. So that means it's a sum of the squares, right? Divided by 2n. Gradient, we now have x transpose, right? X theta minus y. So again, remember x theta is what? Y hat. So y hat minus y, which is what we have been doing, except that it's a vectorized form. So we are doing it all at once. We're doing all the y hats in a single go. We don't have to loop through it or do it one by one as we're writing it. Now we have to do x transpose, because remember, when we are calculating gradients, remember, let's look at this. You always multiply by x, right? You always multiply the gradient. You always multiply the raw residual by x to get a gradient, but the x has to be the x for that particular parameter, right? So here we do that with a transpose, because if you look at it properly, right? If this is x, when you transpose x, right, you now have a situation where you have the rows now become the columns. So the rows will now be each data point, right? While the columns will be each of the separate axes. Sorry, oh, currently X, the rows is each of the data points and the columns is each of the different axes, right? When you transpose, the rows become each of the different axes, right? While the columns become each of the data points. So that's how you need it to be so that you will be able to multiply the raw um the residual, right? So it needs to be that way so that you can multiply the raw residual. Um, Let me see if I can write that properly because I do need to write it so it will be easy to understand. So so the raw residual is you're going to get the raw residual as rows, right? Now you take those rows, you would need to transpose it. So this is what it looks like. Okay, so let's look at this, right? Okay, so if you have initially, right, you are starting off with this. So you're starting off with this. Let me bring this in so that we can easily see. We're starting off with this. This is the starting point for Y and X. Okay, so I'm just putting this in here so that it will help while I do this. So we start off with um X, right? This is X. This is X, which we already have here as a matrix with ones, right? Then for each of the values, we have X1, X2, X3, right? X1, X2, X3. We can just call them X4, X5, X6, but let's just keep calling them X1, X2, X3. But for each of these, right? Remember, this is for the first data point, right? And this is for the second data point, and this is for the third data point. Okay. Now, when you transpose it, if you look at this on transpose X, you see that each row is composed of, the rows are the data points while the columns are the features. But when you want to multiply this P minus Y, which is basically the same thing, right? This is really the same thing for your information. Gradient, like I said, gradient equation for logistics is the same as for linear. We're just kind of using different symbols. But you transpose, remember the X theta is Y hat. And Y hat is made up of the predictions, which in this case, you can see the predictions are Y hat 1, right? Y hat 2 and Y hat 3. So you can see that this is 3 rows while this is, these 3 are for each data point, right? But what we want is we want the gradient to be not per data point, but per feature, right? So we'll have to transpose this X transpose is going to be, you now have the ones up here, right? And then you have X1, all the X1s will be here. So you have 3 X1s here. And then you have X2, and you have X3. So you basically flip it this way. And the essence of doing that is, this is X3. The essence of doing this flipping, but you now see that for this one, this is for data points 1, this entire column, while this entire column is for data points 2, and this entire column is for data points 3. So you have 1, 1. So this will be X1, 1, X1, yeah, sorry, I made a mistake. This is X1, X1, X1. Yeah, that's correct. Oh yeah, okay. So I made the mistake. So this should be, yeah, vectorization can be confusing sometimes. So let me rewrite this correctly. So this is X1, 1. This is X1 again, because when you flip the transpose, each row is for a particular value of X, right? And this is going to be X2, not X1. And this is going to be X3 as well. So this will be X2, but this X2 is for the second data point. And then this X2 will be for this third data point. While here X3 will be for this, and X3 will be for this third data point. So you transpose that, then when you now multiply Y minus Y pred, which is the residual, the raw residual. So you now have a raw residual that is just, let's just call it error, right? So you have error, the raw residual, the error for the first data point, right? The error for the second data point, right? And then the error for the third data point. When you do this matrix multiplication, you will now have xt, which is, since this is a dot product, this is actually a dot product, you now take this vector and multiply it by each row. That's how dot products are done. So if you take this vector and then you sum it, of course, you sum it. So when you take this error and multiply it by the top column, you're going to have error of 1 plus error of 2, right? The second data point plus error of 3, the third data point, right? Taking this and multiplying it this way. That's typically how we do matrices, right? Yeah, you take it and multiply by the second one. You take it and multiply by each row. So in the second one, it will be x1 times error of 1, right? And then plus x2 times error of 2, right? Plus x2, x3 rather. Hmm? sorry, it will be x1 times error of 1 plus x1 2, but it's still x1 anyway for the second data point. Then plus x3, right? X1 3, not x3. X1, right? Still x1, because we are calculating the gradient for x1 here. So it's still x1, but for the third data point, right? Times the error for the third data point. So we just keep going like that. And then this will be x2 now, because we are now doing x2. Yeah, we're now doing x2. So x2 for the first data point times e of the first data point plus x2 of the second data point, you know. It would be nicer if I actually wrote this out. So let me take the time to write this out. So it will be much easier to understand, because the sketches may not be doing very good justice to it. So let me do that. That will take a bit of a while, but I'm going to do it. Let me do it. So if we wanted to do this, right? Um, um, let's see. I'll do an update. I think I'll do an update and share this, because this is it's going to take a bit of time to do this. So um um if we rotate this matrix around, we will now have this. Let me just do it, I guess. Okay, so this is the transpose, right? So this is X transpose now. Um by the way, for those who are wondering, this symbolism is called latex. It's a kind of language that we use for writing mathematical symbols, right? Um, we use it for writing mathematical symbols in Markdown and in other places, right? So it makes it easy for you to do this. So yeah. Um, 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 stop. Okay, so this is X transpose. Um, so if you take X transpose, you will now multiply it by the Y, the predicted Y values, which I can actually do the matrix. So you can see this is you multiply this, right? And what you get is let's do that. So it's going to be another big matrix, right? Um, so it's going to be another big matrix, which is basically taking each of the y's, right, and multiplying. So rather than using y's, this should actually be the error for each of them. So let's just call it error or the raw residual, right? So but we can just call it error. So let me just call it error, right? Let me use E. So you have error, which is the raw residual from each. And so when you do this matrix multiplication, you take this E first and you will multiply it against, you take it first and you multiply it against, so you take the first one, you normally do matrices this way, you take this one and you multiply it here, right? When you do that first multiplication, you will get just the errors, right? Just E1 and E2 and E3, right? So you get E1 and E2 and E3, right? So that's the first one when you do that first multiplication. Then the second multiplication you do, you now take this same vector, right? And you multiply it against the second, you multiply against the second one. So you take this and you multiply it against the second row. Okay? Multiply sum. So I'm actually writing it as if it is a multiply. It's going to give you another matrix, but it's not really another matrix. It's really actually a sum. Yep, it's actually a sum. So you're actually going to sum it. Okay? Then don't worry, it's going to work out well when it's all done. Or maybe I can just do the sum here. Okay, so now it's looking more like it. Now we are going to have the E1s, each of the E1s here. Right? And then we're going to have each of the E2s. And then we're going to have each of the E3s. So this is what I was trying to explain. So you're going to end up with E1 X1 plus E2 error for the first, on this first row. Let's do this for the first row in order to make things easier. Let's just do a one dot. So let's make this so we can at least space it out. And then okay, so yeah, so you can now see we have done this and we end up with this, right? And if you really look at it, you find that this whole line is a sum of the errors or the residual from each data point. While this is the sum of the residual from each data point times the x. So this corresponds to the DC that we were calling DC, right? If you go back up, what we're calling DC, right, up here, or DMO, where we're using mean. So mean is the sum of the raw residual. That's the sum of each error for each data point. So the sum of each error for each data point. While here is the sum of each error times each x. Of course, you will then, that's xt times the residual, right? Which is p minus y. Then when you take that and you divide it by n, that is the average. So you find that just x transpose times the residual gives you the gradient. And then when you're doing gradient updates, you just multiply this residual by, sorry, this gradient, which is the total matrix of gradients, by alpha. So with this, you can see it becomes very easy. You are not going to loop through. It's difficult to understand, but once you have understood it, and that's why I'm taking the time to explain it. Once you have understood and you've gotten the grasp of it, it becomes easy to use because your equation is basically x theta, right? Your cost function is basically x theta minus y, which is the same thing as y pred minus y square. That's the MSE. We already know that, except that it's now vectorized. So everything is combined. But your gradient is x transpose times the residual, which is y pred minus y. And you take the mean of it, right? Along each axis this time around. So you're not just going to do mean, but you're going to actually do a dot function and divide it by n. Gradient update, you do that. Now you can see that when we come to logistic regression, we can use exactly the same thing. So with logistic regression, we are still using the same x theta, right? Which is y, right? But we pass it through a sigmoid function. So you now get 1/1 plus epsilon, right? Or E minus x theta, which is the y hat. That is the logistic equation, which is P. And then the cost function is the negative log likelihood, which we see here. And it's still going to be, this is a long form, right? But the short form would simply y times ln P plus 1 minus y times. So I wrote this in long form, but in the real short form, it's still the same thing. And then the gradient is exactly the same as the gradient for linear regression, right? Except that, instead of using x theta, here is sigma x theta, sigma function or sigmoid of x theta, right? So it's the same thing, x transpose times that. That p minus y, which is y pred minus y, that is, of course, the residual. And then you still multiply it by the transpose of the x divided by the number of data points, right? And you get the gradient, average gradient per parameter. And then you do the batch gradient updates the same way. So with that knowledge, let us try redoing this same thing with a vectorized implementation. So if you look at a vectorized implementation, the sigmoid function is the same. The sigmoid function is the same. Now, but when we are doing the training function, we now have a vectorized version of x. Of course, the x is already vectorized version. You can now see that z is x dot w. X dot. So use a dot product, which is this, right? X dot, w and theta are the same thing, basically. Because I had already initialized w to be zeros. And zeros should have the same number of elements as the number of features. The number of features, D is the number of features, which is the number of X independent variables plus 1. Because we want to add extra 1 for this. We want to add extra 1 for the biases. So we want to add extra 1 for the biases. So that's why we would always have the D, which is the number of features, as number of independent variables plus 1. Okay. That number of D is the number of features. N is the number of data points, which is the batch size or the number of batches or the number of items in the batch gradient descent. So the number of parameters should match the number of features that you want. That's the X number of X's plus 1. Okay. So we do that here. Then we have a previous loss of infinite. We give an infinite value because we are basically saying we start with infinity. The loss is supposed to go down. This is the same way we are tracking losses. So now we predict with the dot products of x dot w, which is what, or x dot theta, which is what we have here, right? Then we do a sigmoid on that intermediate value of Z, and we get the P, which is a probability. This probability is not a probability distribution, basically Y hat, that corresponds to each Y. We now have this thing we call epsilon. Epsilon is basically a value that we use to avoid zero errors. I'll explain that later. But you can now see the negative log likelihood equation here. So this is the first part of it, which is for when you are predicting ones. So we are doing NP mean. We're now doing a mean. And then this is the first part of it. Y times log of P. Again, the epsilon, like I said, is so that I don't do log of zero. If P were to be zero, you have log of zero. Log of zero, like I say, is minus infinity. It's a very high value, and it will throw errors in your computer, in your program. Most compilers will throw error when you try to take log of zero, because log of zero is equivalent to division by zero, right? So we just add this little epsilon value, which is a very low value, is 1 raised power minus 12, 10 raised power minus 12. So this is like 0.000 up to 11 zeros and then 1 at the end. So it's a very low value. It's so low, it will not affect anything you are doing. So we now have this. Then we add the second part, which is the part for when you are trying to predict a zero. So it's 1 minus y times log of 1 minus the predicted value, which is 1 minus y hat, right? This is this. But again, we also add the epsilon to guard against division by zero or log of zero, okay? So with this, you have that. That is the value of the negative log likelihood. We now have this additional thing that is added. We call this regularization. I'm going to talk about regularization later on, but regularization is to help with overfitting, because there were a few questions of overfitting and so on, right? But regularization helps with that because it does not allow your loss to become so attached or so tied only to the parameters, right? It brings a bit of randomness into your loss so that to prevent overfitting. We'll talk about all of that. We'll go to regularization. So you can see this loss, you are using a vectorized version, right? And you can see that there is no looping here. And we have a single equation for loss rather than here where we had 3 equations for loss. We actually, okay, well, we still had one here because, well, we were doing a semi-vectorized and we are taking the mean. But when we do the gradient, we had to do 3 different ones, right? But here, when we are doing the gradient, we simply use that dot product. First of all, we transpose x dot t. So when you are using numpy, you can use dot t to transpose, right? So x dot t, uppercase t. This will transpose the x, just like to match the mathematical symbol of xt. So then we do a dot product of that with the residual, the raw residual, which is p minus y, right? Which is the sigmoid, the predicted value. And then the gradient is also divided by this n, right? It's divided by n to give you the average for each. So you can see we're not using mean here because mean would basically have the mean of all of them, unless you do mean and you specify the axis, which is another way of doing it. You can do np.mean and specify axis equals to axis should be 0. So we take the mean along the 0 axis, which is along the row axis, and that will give us the same thing. But here we divide it by n, right? And when we divide by n, we are basically going to calculate the mean of the gradient for each term, And then you have this last thing that's added here. Again, it's a L2 regularization. We'll talk about that. So this is just like we were regularizing, right? With this, we also have to, when we are regularizing the gradient, when we are doing the gradient, we have to regularize by the gradient of the of this function, this regularizing function. So with that, you have a gradient. This gradient contains all of the gradients for all of the data points. Sorry, for all of the parameters. And then you just do a single parameter update. So the other, when we're doing semi-vectorized, we had 3 or 4 parameter updates. But here we have just one because this gradient is matching W in its shape. So we just multiply the learning rate, which is a single value, by all of the gradients, and we use that to update. And that's it. So you can see how much faster it is, and it's easy for you to read the code because it's all really quick. Now, the other interesting thing I would like to do here is how long would this take, right? Compared to the other one, we can measure time and say start equals time.time. Then when we are done, before we return the value, we can now say end equals time.time. And then we can print. So this is a way of doing it, right? Same thing. Of course, I have to call the function here. So I've done the function itself. Then I now start with the data and I basically call the function. So let's see how this goes. I've added time to this now and I'm still using the TPU. So let's see how fast the TPU does this, right? We stack and then we run this. Okay. You can see the time taken, 0.15 seconds. Are you not amazed? 0.15 seconds. The vectorized version takes 0.15 seconds. Okay, well, this is 5,000 epochs. So let me do 1,000,000 epochs just to be sure that we are doing the same thing. All right, 1,000,000 epochs. Still faster, 0.27 seconds. Now let me run the whole thing, right? Let me run the entire thing from scratch. And I'm going to check the time it takes. So you can see why we use vectorization. Vectorization is going to speed up convergence. If you write your training script and you don't vectorize it, you're going to get very slow performance, especially on all of these accelerators, the GPUs and TPUs. On the CPU, it might be almost the same speed, but on GPUs and TPUs, because you're not really looping through them, you're passing an entire batch into it, right? You will get faster speed. So this is when it just finished this one. It took 31 seconds. And I'm using a TPU, right? I'm using a V5E1 TPU, right? It took 31 seconds to use the partially vectorized method. Now let's go look at the vectorized method. Vectorized method is done in 0.274 seconds. So you can now see why we like doing this. And I really took the time to explain this so that we can understand why vectorization is important. The difference in time, you can easily calculate. Let's calculate the difference in time. I'm going to just copy the values. So and then we can scale it up, and then you see what impact it has on your code, on how fast you can train your models, right? So we can say X using semi vectorized seconds time using semi vectorized is this, right? But the time with full vectorized is what? Uh, Funny enough, the interesting thing is that for the full vectorized, we even printed out the loss in each epoch. But in the semi-vectorized, we did not even print out anything. While we were in this loop, we did not print out. And you know that printing stuff takes a bit of time, right? We didn't print stuff. It took 31 seconds. But here we were even printing out, right? The loss at each point, and it took 0.2747 seconds. So these are practical machine learning. When we talk machine learning ops, this is now what you start thinking about. So the percentage, yes. Let's just see this. This is 100 times speed up, 100 times speed up. So what this means effectively is that the thing that you have used vectorize to train in 1 day, you will use 4 months to train using non-vectorized code. Okay? If you wrote non-vectorized code and, or rather, if you use vectorized code and it took you 1 day to train that model, that same model with non-vectorized code will take you 3.5 months or almost 4 months to train. This is a very important distinction, very important. That's why I said vectorization is very important to learn. Okay, so are there any questions? If there are no questions, I will end the session by introducing the next round of topics that we will be handling. So we have done linear regression with single variable. We've done um, linear regression with multiple variable. And we've done logistic regression with multiple variables. I was hoping we could do polynomial regression, but we've kind of run out of time. So I'll leave that as an exercise. I will prepare a lecture note on that as well and share so that everyone can read through it. And if you do want to go into it, maybe we can look for a time and I can walk everyone through it. But this week, we really are going into using the libraries, specifically sklearn, right? And then we're going to look at other methods, other architectures. Generally, we're just going to look at different architectures, different types of, models and how we can use them to solve all of these regression problems that we talk about, right? So we are first of all going to look at we are going to look at trees and then random forests. We are going to look at SVMs and let me bring that up quickly. Give me a second.